Hi, I'm Frank O'Brien, and welcome again to the InfoAge Spaceflight Lecture Series. First and foremost, I hope everyone, and you and your families, have all been safe and healthy during this pandemic. This month's lecture is about the planet Venus, that bright shining star that we see early in the morning or sometime a little bit after dark. It's been a mystery for ages, with its clouds hiding even the most basic details about itself and its origins. Early in the space program, both NASA and the Soviet Union launched missions to Venus to pull away its veil and discover what the planet was like. Unlike many of the early space missions which ended in failure, most flights were spectacular successes. Still, the atmosphere around Venus thwarted some of the most basic investigations, forcing scientists to come up with new ways of studying the planet. We'll be talking about what we've learned and what the future will bring. We'll also be doing something a little bit different from our previous lectures. We have a lot of material to cover, so it's much easier to break this talk up into two different parts. Each will be about 30-35 minutes, and the second part is going to be done as a separate video. Now, before we start, just a few words about me. Many of you already know this, but for about 25 years, I've been one of the editors of the NASA website that extensively documents the Apollo moon landings. And about a decade ago, I was accepted as a NASA Solar System Ambassador. There's about 1,000 of us all across the U.S. who go into communities and share insights on the NASA mission. I've talked at schools and service groups and libraries and museums, I've talked everywhere. We're often the first opportunity for those in the community to go out and interact with someone who has direct connections to NASA. This is a fantastic all-volunteer program, and no tax dollars are spent on it, and of course, we never accept any kind of compensation. The history of observing Venus is perhaps as long as astronomy itself. But the concept of Venus as a feminine construct is part of Roman mythology and was readily adapted in Europe and in the West. The Greeks imagined Aphrodite, the goddess of love and beauty and fertility. Because Venus is so visible, other civilizations had their opportunity to chime in. Many of their representations were masculine or even fantastical. In early Central American societies, Venus was apparently related to the god Quetzalcoatl, I think I have that right, who was a feathered serpent. And as a final twist, with Venus sometimes appearing in the morning and other times in the evening, it was often thought to be two entirely different planets. Because it was impossible to understand the environment of Venus before the age of spacecraft, there was huge speculation about what the surface was like. Observations made as far back as 1761 presented the hypothesis that Venus had an atmosphere, and from there, it was off to the races. It was easy to assume that Venus would be a much hotter version of the Earth since it was closer to the Sun. Next, the surface was obscured, and the reasoning went that, well, it's obscured by clouds, and this is why we can't see all the way down to the surface. That turned out to be one of the very few correct facts. Another reasonable guess was that since the clouds are so reflective, much of the sun's energy would be reflected away, leaving Venus with a surface temperature that would be less than its close proximity to the sun would suggest. Now, Of course, since clouds are made out of water, that must have meant the environment must have been hot and humid. And what kind of places are hot and humid? The tropics, of course. So, working down this innocent but completely incorrect line of logic, it stood to reason that the surface of Venus was covered in lush tropical jungles. And of course, with the jungles, there had to be indigenous peoples, and not to mention fantastical beasts. These Victorian fantasies were decades before the advent of pulp fiction magazines, which then took this genre to, well, a completely insane, wild extreme. But still, we're stuck with the fundamental problem to the study of Venus being its clouds. The view of Venus in wavelengths that the human eye uses really is essentially featureless, making really for a pretty boring planet. Until the middle of the 20th century, this was pretty much all we could see. Prior to the advancements made since the Second War, astronomers strained to see any detail that they could, and they were usually pretty disappointed. Basic information, such as the size of the planet and its orbital period, were pretty well known, but even such basic details as the length of time the Venetian day was, well, their estimates were all over the place. Eventually, the use of spectroscopy made it possible to get us some details about the composition of the atmosphere, which opened up huge amount of educated guesses about what the surface is really like. Because the clouds prevent our eyes from revealing any of the surface details, we need to use other means. The best, and honestly, perhaps the only way to penetrate the clouds and resolve any kind of detail is going to be with radar. There's been some successes in using imaging in the ultraviolet to see the surface, but again, this hasn't been hugely successful and it doesn't work everywhere. So, any images, and I'm going to be a little bit hesitant to call them photographs, that we have of the surface will be from the Magellan probe in the early 1990s, plus a few from the Soviet Venera probes before that. Although these are spectacular, they're not especially high resolution, at least at the level of resolution that we're used to seeing from the spacecraft that go to the Moon and Mars. Later on in this talk, we're going to be talking about future missions and how we're hoping to fix that problem. While nearly impossible to see with the naked eye, Venus does go through phases just like the Moon. Galileo, in some of his earliest observations with a telescope, discovered this as early as 1610. These observations disprove the idea that the Earth was at the center of the universe and the Sun and the planets were revolving around the Earth. The Copernican model, with the Sun and the planets, including the Earth, revolving around it, was the only possible explanation. Now, as Venus orbits the Sun, the perspective from Earth changes. As it moves toward its closest approach to Earth, more and more of its sunlit side faces away from us. The effect is we see Venus becoming a smaller crescent, exactly in the way we see the Moon move into its new moon phase and slowly out of it. The opposite situation, where Venus is on the far side of the Sun from us, most of its sunlight surface is visible, and we see a full Venus again, just like the full moon. One thing that you might notice here, which is making sense because when you think about the geometry of it, of the planets in their orbits, Venus is at its smallest apparent size when it's near its full phase. At this point, it's about 160 miles away on the other side of the Sun. At its closest, Venus is as close as 26 million miles away, far closer than Mars, and this makes for it to be appearing as a much larger planet. Unfortunately, we're looking mostly at the side that's not lit by sunlight. The phases of Venus are easily seen, even if you only have a modest telescope or even just a good set of binoculars. And you ought to check it out. It's really pretty spectacular. This isn't normally the kind of chart that we're used to showing about the planets and the Sun, but it shows an interesting phenomena. Here, we're showing the path of the Earth and of the Sun and Venus from the perspective of Earth at the center. Importantly, this shows that the path of the Earth through the Earth's sky that Venus travels repeats on a very, very regular cycle. During a 5-year period of time on Earth, Venus orbits almost exactly 8 times, varying only 2 or 3 days over those 5 years. This is what's called an orbital resonance between Earth and Venus, and it's a property that we see of many of the moons of Jupiter and Saturn, as well as Neptune and Pluto. With Venus orbiting in such a lockstep with Earth, its path, the path it takes through the sky repeats over the years and is very, very predictable. At first glance, the orbit of Venus itself around the Sun isn't particularly interesting. A Venetian year, the time it takes to travel around the Sun, is a little less than 225 Earth days. Its orbit is almost perfectly circular at a distance of about 67 million miles from the Sun. Now, a really simple question should be, how long is a day on Venus? A complete oddity is that Venus rotates backwards compared to the directions of the other planets. Its rotation is also the slowest in the solar system, taking 117 Earth days for the Sun to pass over the same line of longitude, or your house if you want to use that as a measure. If this sounds oddly specific, it is. Next, we consider that orbital period, the one of 225 days. When these two motions are combined, the effect is that the Sun will rise in the west and set in the east, completely opposite from our experience on Earth. Now we're going to complicate things even more. There is a second, equally valid way of measuring a day, which is the time it takes for a star to be at the same position overhead during each rotation of the planet. On Venus, this is 243 days, and it's called a sidereal day, and it's longer than the Venetian year. If these two ways of measuring a day sound confusing, well, perhaps they are. But on Earth, we have the exact same situation. We consider the Earth's day as being 24 hours long. But our sidereal day is actually 23 hours and 56 minutes. We adjust our calendars to account for our position in the solar system by inventing the leap year, adding a day every 4 years. Now, here's your homework assignment for tonight. With a day that's longer than a year, how do you create a calendar for Venus? Be sure to show your work. The orbit of Venus, relative to the plane of the Earth's orbit, is inclined a little less than 4 degrees. Now, that isn't a lot, but it means that lining up the Sun, Venus, and Earth is a rare event. Observing this event, called a transit, is where Venus appears to cross the surface of the Sun. 2 transits occur within a few years, but then we need to wait another century or so before those 2 transits repeat. While it may seem that a transit is just an interesting astronomical curiosity, huge advancements in our understanding of the solar system resulted in studying them. The transit of 1639, nearly 400 years ago, gave astronomers their first reasonable estimates on the size of the solar system. Over a century later, and with better telescopes, the first indications of an atmosphere on Venus were seen. And this reinforced the idea that Venus was more or less like the Earth. Observations conducted in the 1800s resulted in very accurate estimates in the distance of the Earth from the Sun, and refined the distances of other planets as well. Unfortunately, the most recent transit of Venus was in 2012. And unfortunately, the next one won't be around for at least another 100 years. So much has been written about Venus being the Earth's twin. Well, let's talk about that. Maybe evil twin is more appropriate. Venus is just a little smaller than the Earth, only a few percent smaller. Its density is just about the same as the Earth's, and we believe it has an internal structure that's comparable to the Earth. This means that there's a thin crust, a relative liquid and fluid mantle, and a large core made up of heavier elements. Its surface gravity is only a little less than the Earth, so you would feel about 90% of your Earth weight. That is, if you could make it to the surface. We're going to be talking about the atmosphere and the structure of Venus in a lot more detail. But here's a spoiler. You don't want to build your vacation home there. One important point should be mentioned here. As we will see, observing the atmosphere and surface of Venus isn't like studying the Earth. Opaque clouds block any direct view of the surface, and the atmosphere temperature and pressure makes it nearly impossible to send probes that will survive more than an hour or 2. As a result, we're forced to view the planet through very narrow windows, and by the very few probes that have made it to the surface alive. We'll complement this data with the extensive models used on Earth to create a surprisingly comprehensive picture of the planet and its processes. At the beginning of the 1960s, after the first wave of successes and accomplishments with satellites around the Earth, the United States and the Soviet Union turned their attention to Venus. Given the primitive state of the art by today's standards of spacecraft and rockets, it's not surprising to realize that, well, most of those early missions were failures. The complexity of the spacecraft was pushing the limits of the possible, and the rockets were far from the levels of reliability and accuracy that we take for granted today. But in 1962, NASA launched Mariner 2 to Venus with the objective of solving a huge, long-running controversy among scientists. Years of Earth-based observations couldn't resolve one of the most basic issues, and that's of the temperature of Venus. It seemed impossibly high. Was this a result of a very hot atmosphere and a relatively cool surface? Or is the surface itself broiling hot? Also as important, how dense is the atmosphere? Once on its way, Mariner 2 had its share of issues that easily could have doomed the mission. Ground controllers struggled with overheating, communications failures, attitude control issues, none of which were surprising for NASA's first interplanetary mission. However, when the key moments of that first encounter arrived, Mariner 2 performed magnificently. One of the most important sets of measurements was completely conclusive. The surface, not the atmosphere of Venus, was breathtakingly hot, well over 400 degrees Fahrenheit. Of course, future missions would find this value really quite low. Mariner 2 also found that the atmosphere is incredibly dense and thick, which again, scientists were happy to have their suspicions confirmed. An even more surprising finding was that the nighttime side of the planet was just as hot as the sunny side. With this information, scientists started planning, new missions for their, ongoing exploration of Venus. The Soviet Union, flush with its early successes in space, planned ambitious missions to Venus. It made sense. Venus was technically much easier to reach than Mars, and any new information on a planet would be a breakthrough. For 6 years, the Soviet Union launched 11 progressively more advanced missions to Venus, all of which ended in failure. Finally, Venera 4 was launched with the goal of dropping an instrumented capsule to directly sample the Venetian atmosphere. Finally, the Soviet Union had an outstanding success to show the world. As it fell slowly through the atmosphere, the probe sampled the composition of the atmosphere, which was found to be about 90% carbon dioxide. With all the unknowns about the temperatures and pressures of the full atmosphere, the design of the probe made reasonable assumptions about the environment. Unfortunately, Venus turned out to be far, far harsher, and the probe failed at an altitude of maybe 15 miles up. Still, this was an amazing achievement for the Soviet Union. During the same window of opportunity for missions to Venus, NASA launched Mariner 5. Mariner 5 was intended as a cheap and fast mission to Venus and used the spacecraft that was originally built as a spare for the 1964 Mars mission. Modified to survive the higher temperatures of the inner solar system, and with some instruments either updated or removed that they weren't necessary, Mariner 5 reached Venus only a few days after Venera 4. In one of the most important examples of early international cooperation at the height of the Cold War, the United States and the Soviet Union eagerly exchanged their data on the missions. Such an exchange of scientific knowledge allowed for far, far greater understanding of the planet. After the combined successes of Mariner 5 and Venera 4, budgets and changing priorities forced NASA to move away from Venus exploration and to focus on Mars instead. The Soviet Union, however, charged headlong into missions to Venus, all the while stinging from their repeated failures at Mars, continually updating their now proven Venera lander with a steady stream of successes. The next missions to Venus, Venera 5 and Venera 6, were simply intended to sample the atmosphere's temperatures, pressures, and compositions, and they confirmed all the results of Venera 4. The next mission, Venera 7, became the very first spacecraft to land on Venus. Despite troubles with pointing its antenna, it was able to return data from the surface for about 20 minutes, revealing a pressure of about 1,300 psi, or about 92 times that of the pressure on Earth. and temperatures that were nearly 900 degrees Fahrenheit. This is a breathtaking amount of temperature and pressures, but it did confirm what scientists had been suspecting. This showed that there is no life as we know it on Venus, as even life that exists in extreme environments would quickly perish on its surface. Following Venera 7, the Soviet Union continued with a series of probes and landers for the next 11 years, with most of them being really pretty successful. The science that was returned by the landers was especially full of new data on the composition of the atmosphere and the nature of the surface itself. Here is a mock-up of one of the spacecraft, Venera 13. The spacecraft itself is huge and weighs in at almost 10 tons at launch. The lander itself is in the little brown sphere at the top. This would detach from the main spacecraft and plunge through the atmosphere. Once through the worst part of the entry sequence, it would break open and deploy a parachute to slow its descent. Here we have a picture of the Venera 13 lander itself. You can see it's really not all that big, although it weighed in at nearly 1,700 pounds. Much of that weight was from a thick spherical shell inside that protected the instruments from the heat and pressure of Venus. Now, what's particularly interesting is that there's the large disk at the top of the spacecraft. We would normally expect that a spacecraft going to land on a planet with an atmosphere would use a parachute to slow the descent all the while down. This works well on Earth, Mars, and even Saturn's moon, Titan. But a parachute isn't needed for the final part of the descent to Venetian surface. In fact, for those early landers, it creates more problems than it's there to solve. Using a parachute will slow a spacecraft into a nice, slow, gentle, long descent, and that sounds like a good thing, right? But at the blast furnace temperatures of Venus and the crushing pressures, any parachute would simply melt away early on, leaving the probe to just simply free fall to the ground. At the same time, designing a spacecraft and its instruments to withstand that extreme environment is really pretty hard. At best, the longest the scientists could expect a lander survive was only a few hours, and probably quite a bit less. So engineers came up with an ingenious solution. After descending through the relatively cooler parts of the atmosphere and into the hot, thicker layers, the lander was cut loose from its parachute to descend on its own. Because the atmosphere is so thick, a simple metal disc on the top of the lander was used to slow the descent. The atmosphere was so thick that this disc effectively acted as its parachute. One of the most amazing accomplishments of the Soviet landers was that they quickly took pictures of the surface before the spacecraft perished. With the surface completely hidden by opaque clouds for us, these images were the first time that the landscape of Venus was ever revealed. Since the spacecraft were targeted for relatively flat terrain, it's not a surprise that we don't see much in the way of craters, hills, mountains, or other features, although other pictures do show them. A few things to notice in the pictures. The surface is essentially flat, with a layer of volcanic material called basalt, whose existence was not a surprise to scientists. And the colors in this picture are very close to what you would see on the surface. Virtually all the green and blue light is scattered out, leaving only an orange glow illuminating the surface. It's also quite dim. Even though Venus receives nearly twice the sunlight as does Earth, the clouds reflect about 3/4 of that back into space. Thick clouds absorb and scatter the remaining light, leaving the landscape illuminated as if it was only twilight here on Earth. In 1978, the Pioneer Venus mission was finally launched. This was NASA's first return to Venus in many years. This was a big, ambitious mission whose goals quickly exceeded the ability for current rockets at the time to launch a single spacecraft. So, the mission was split into two complementary spacecraft. Pioneer Venus was composed of an orbiter spacecraft, which studied the clouds in the local space environment, and a multi-probe mission, whose goal was to carry probes into the atmosphere that reported on temperatures, pressures, and composition. Given that this was a rare opportunity for a mission to explore the atmosphere directly, 3 probes were assigned to study distinct areas of the planet, simply referred to as day, night, and north, representing the areas that they were targeted for, and were designed to build a comprehensive view of the atmosphere. A far larger 4th probe, with a much more comprehensive set of experiments, was also dropped into the atmosphere. The results were quite a surprise. Unlike the Earth, where there's large variations in the temperatures between day and night in the polar regions, there was very little difference between what the probes reported on. This had huge implications on the climate models of the planet that would be constructed. The orbiter, which arrived just a few days before the multi-probe mission, lasted about 14 years and returned the very first topographic map of the planet using a radar altimeter. Although this map was really terribly low resolution, with features no larger than 50 miles across visible, it revealed a complex topography of the surface. Its instruments also studied the compositions of the clouds and confirmed that the planet has no magnetic field. This would have huge implications in later studies. This lack of magnetic field would have incredible implications of the evolution of Venus, and we're going to be talking about that later. Up to this time, virtually all previous missions studied Venus were operating under the same handicap. There really wasn't anything to see. With a planet covered essentially in impenetrable clouds, there was not much else to see aside from a white disk. The Soviet Venera probes made spectacular breakthrough by returning photographs of the surface, but aside from low contrast images of the clouds taken through special filters, the clouds around Venus successfully veiled its secrets from us. Although the clouds are opaque to visible light and most infrared light, they're quite nearly transparent to radio waves at radar frequencies. The Pioneer orbiter demonstrated that using a radar was possible, but to be useful, a far higher resolution map was necessary. Eventually, a new mission named Magellan was designed with a single purpose. Using a synthetic aperture radar, Magellan was to map the surface in far greater detail and provide 3-dimensional views of the planet. Magellan was conceived during the era of really quite tight budgets at NASA, and so many of its systems were cobbled together from spares for other missions and parts that they basically had sitting around. For example, the main spacecraft body and the large dish antenna were leftovers from the Voyager probes, and many systems were spares from the Galileo Jupiter mission. Launched in 1989 by the space shuttle Atlantis, Magellan orbited Venus for 4 years and returned incredible imagery of the Venetian surface. With the exceptions of a few images of the landing site from the Venera landers, all the images of the surface that we're going to be seeing in this talk are all from the Magellan mission. You'll notice that all the color schemes are standardized, ranging from a brownish red to an almost golden color. Altitude information is used to create that sense of height, and it's exaggerated about tenfold to make the detail more pronounced. One of the things that both Pioneer and Magellan showed is that Venus is really pretty flat, making important features difficult to pick out. By exaggerating that vertical scale, the photography reveals itself much easier. After the Magellan mission, it was over a decade before Venus had another long-term visitor from Earth. The European Space Agency launched their Venus Express spacecraft, carrying with it an extensive array of instruments to study the atmosphere and the space environment around the planet. While such a long delay is unfortunate, it allowed scientists to review the existing data from the previous missions, and they came up with new questions that needed to be answered. For 9 years, Venus Express studied the processes within the atmosphere and revealed the nature of its fantastically high winds and the fate of water on the planet. Researchers were also able to confirm the climate models of the effects of carbon dioxide on Earth by comparing them to observations on the atmosphere of Venus. A surprising finding was that although Venus does not have an internally generated magnetic field as Earth does, it creates one through the interaction of the Sun and the upper atmosphere of Venus. So, these are the major missions to Venus over the last 60 years. Now, for just a moment, think of that. We've been exploring Venus for 2 generations. After all that effort, with about 25 successful missions by a number of countries, what have we learned about this cloud-draped world of Venus? We're going to take a break right now so that we can catch our breath, and we're going to return with part 2. I hope to see you then.